And now we get to break the rules. So I told you that we will not violate the octet rule. You can only have 8 electrons around something, never more than 8 electrons. Sometimes things like to have 6 electrons. This video is about expanded octets. So, an expanded octet is when we are drawing a Lewis structure that shows more than 8 electrons around something, and we do it only for certain elements, and we do it for a specific reason. So, you can only do this for elements that are in the third row and below. So, I have third row and beyond. Same thing, third row and below. Now, that's the majority of the periodic table. However, it's not the majority of the molecules that you'll be drawing. We draw a ton, and we have a ton of important molecules that use the elements in the second row, which is why we spent all of this time talking about not violating the octet rule until you get to this video. But right, boron, carbon, nitrogen, oxygen, fluorine, those never more than 8 electrons. You cannot violate the octet rule. Silicon, phosphorus, sulfur, chlorine, and everything below that, absolutely. You can violate the octet rule if you need to. So the reason that we give for being able to do this is that if we're at n equals 3, it means we have access to the d orbitals, which means that in a valence shell, we have access to more orbitals in which we can put electrons compared to the things that are in the second row where you have 2s and 2p, right? That is your valence shell, and that's it. Now, in reality, this is not really a true statement, but it is a piece of information that will help you remember which ones we can use. And right, Lewis, this is a Lewis model. It is a model of bonding. It's not perfect, but it's going to work so well for so many things that we need to do and help us communicate. So that's why we're still learning it, and we're still going to use it. So the reason that we expand octets when possible is to minimize formal charges. So we're going to do perchlorate as an example so that you can see what it's like with and without expanding the octet. So valence electrons, chlorine has 7, each oxygen has 4, and it's negatively charged. So I have 32 electrons to put into this molecule. Chlorine is listed first, so it's in the middle, and then I have the 4 oxygens connected to it. And then I go through and I put lone electrons around each of the oxygens. And after doing this, right, I had 8 in my bonds, and then I go and I add 2, 4, 6 to each oxygen. That puts me at 32 electrons. Everybody has an octet, even chlorine, because it has those 4 bonds. And I mean, it seems there's a lot of lone electrons hanging out, but this is what we got. So my Lewis structure isn't done yet. I need to calculate formal charges and put them next to the atoms. So oxygen with 3 lone pairs, so 6 lone electrons and 1 bond, that's a negative formal charge. So every oxygen has a negative formal charge. And then chlorine has 4 bonds, and that's it. That gives chlorine a +3 positive charge. So I have a formal charge on every atom. Chlorine has a charge with a magnitude of 3, and it's positive. So electronegativity-wise, it's about the same as oxygen. So none of these things are going to want to have a positive formal charge, but a +3 formal charge on chlorine, it looks horrible, right? It's on this electronegative end of the periodic table, and now it has a positive charge that also has a magnitude of 3. So let's push some electrons. You could take this step by step, push 1 lone pair to make a double bond, recalculate. I've gone with the extreme version. So what happens if we push a lone pair from every oxygen. Let's give every oxygen a negative, or give every oxygen a 0 formal charge. Okay, so this is my first structure that I have. So I have chlorine in the middle, a double bond to every oxygen, and when I calculate my formal charges, this gives chlorine the negative formal charge, and all of my oxygens have 0. Well, okay. My other option that doesn't put a negative on chlorine is that I push electrons on every oxygen except for 1. And so I would have a chlorine with 3 double bonds to the oxygens, and then 1 oxygen with a single bond. Each oxygen that has a double bond has 2 lone pairs, and my oxygen with a single bond has 3 lone pairs. So that means that my negative formal charge is on the oxygen with the single bond. Okay, so choosing between these two, if you look at the actual electronegativity numbers, I said they were about the same, which they're close. Probably neither one of them wants to have a positive formal charge, if at all possible. But based on the actual numbers, oxygen is 3.5, chlorine is 3. Oxygen is more electronegative. That makes the structure on the right the best structure because it puts the negative formal charge on the more electronegative atom. Now, why that oxygen? It was just by chance that it was the oxygen connected to the right that ended up with the single bond and the negative formal charge. We could have left that negative formal charge on any of the oxygens, which means we have equivalent ways that we could draw this best structure, so we will have equivalent resonance structures. I've got these oxygens labeled A, B, C, and D so that 1, we can tell them apart and I can talk about them, and 2, you can see that the atoms don't move. If you are tracking oxygen C through all of these pictures, it's always in the same spot. Only the electrons are moving. So I've got my best structure redrawn here as the first thing. Single bond to oxygen, negative formal charge, that is oxygen C. Resonance arrow. Instead of putting my single bond there, I could have put my single bond between chlorine and oxygen D, and double bonds in all the other places. Puts my negative formal charge on oxygen D. Or, set of resonance arrows, I could have put that single bond between chlorine and oxygen A, which is the one on the left. Negative formal charge on that oxygen, double bonds for the rest. Or I could have put that single bond between chlorine and oxygen B. Right, none of my atoms moved. I just moved the electrons around. There were technically 4 different places I could have put that single bond and had the same types of bonds between the same types of atoms, minimized the formal charge with the negative formal charge on the more electronegative atom. So all 4 of these structures together with the resonance arrows, that's my final answer. If you were asked to write the best Lewis structure and any equivalent resonance structures for perchlorate, it's this entire line. Okay, we are going to talk about radicals in this video as well. A radical just means that it has an odd number of electrons. So we will have to try to figure out where to put that lone electron. So I have NO here as an example, and there is a rule for radicals, which is that you put the single electron on the less electronegative atom. 99.9% of the time, if you don't remember that rule, it's fine, because you can just use the Lewis structure rules we have used so far, where you minimize formal charge to accomplish the same thing. If you have things that are equivalent in their electronegativities, um, then it depends on the molecule. I think the examples that I've seen of this are that you would probably put it on the central atom, or something fancier is happening and you're in orgo and you should go ask your orgo instructor. Okay, let's do NO and look at what we get. So 5 valence electrons from nitrogen, 6 from oxygen. It's 11 valence electrons. Um, you can pause here if you would like to try to put this together. I'm going to jump to our final option, which is nitrogen with a double bond to oxygen. And then we can either put 2 lone pairs on oxygen and then a lone pair and a single electron on nitrogen. Or on the right, I have nitrogen double bond to oxygen. I could put 2 lone pairs on nitrogen and a lone pair and a single electron on oxygen. So when you go through and calculate the formal charges, for the structure on the left, nitrogen with a lone pair, 2 bonds, and a single electron, that's a 0 formal charge. And oxygen with a double bond and 2 lone pairs, that's a 0 formal charge. If we calculate the formal charges on the resonance structure on the right, nitrogen with a double bond and 2 lone pairs, that's a -1 formal charge. And oxygen with a double bond, 1 lone pair, 1 single, that's a positive formal charge. So minimizing formal charges, well, first just means getting 0 formal charge. So that gives us the structure on the left. Plus, oxygen is more electronegative than nitrogen. So the positive formal charge on an oxygen, not ideal. So we're choosing the structure on the left as the best because it minimizes the formal charge. It also then follows this rule for radicals, which is that you put the single electron on the less electronegative atom.